want to review and go over what we looked at yesterday in terms of the properties of the acids and the bases. So many of you completed the lab, many of you handed it in various ways, on paper, etc., or online. And I've marked most of those, but I'm still going to hang on to them for the last few that might come in. But remember, we did a bunch of various tests. Listen to me. Okay. We did a bunch of various tests, and I just want to see whether you remember what some of those tests were. And then remember, there was a couple of slides that I wanted you to write down, and I'm just going to put them up here in a minute. Let's talk about the acids. Does anybody remember some of the things that the acids would do? The acids, what did they do? Tell me what they did to certain things. I don't care which things. What do you got? Well, yeah, they are corrosive, but we never tested that. I guess it did corrode the magnesium. Correct, it is corrosive. How did you know that it was corroding the magnesium? What did you see that that indicated to you that there was that corrosive reaction going on? It was fizzing, producing bubbles. Actually, those bubbles were hydrogen gas. We could have tested that with a little splint and see if it went pop, but we didn't do that. What else did the acids do? What else did the acids do? Come on, we all did this. You all remember? Think about the acids. Hydrochloric acid, sulfuric acid. What else did they do? Come on, for some of them, you got a 50-50 chance. Yep. It turned the litmus indicators red. Correct. The blue litmus became red, and the red litmus, well, it stayed red. So the litmus paper stayed red. What else did it do? What else was true about it? Anybody remember? The acids? Yep. The pH levels were low, 1 and 3. I saw a lot of 1s and 3s, all right? So the pH levels are low. They're lower than 7. Excellent. What else did it do? We also reacted some sodium bicarbonate. What did it do to the sodium bicarbonate? Yep, that. It fizzed. That gas that it produced was carbon dioxide. If you've ever done the reaction, the volcano reaction, where you react sodium bicarbonate or baking soda with vinegar. Has anybody ever done that before, baking soda and vinegar? Bubbles all over the place. That's the exact same reaction we did, except instead of using vinegar, we use simply different acids. I'm still here. I'm going to be here for 75 minutes. Okay. So it also causes that to fizz. Did we test anything else? Oh, some indicators. What did it do to the phenolphthalein? What did the acids do to the phenolphthalein? Nothing. Wasn't very exciting. In actual fact, it's colorless, we say, right? That it has no color. What about for the bromethymol blue? What did it do for the bromethymol blue? It looks like only Pat and Zach and Kate have done the lab. Oh, here we go. What do we got? It turned yellow. Excellent. The bromethymol blue turned yellow. Excellent. Very good. How about some base stuff? Contrast that. What did the base do with the litmus? Yep. Turned it blue or it stayed blue. What did it do with the phenolphthalein? Yep. Not really, I don't know if I'd say blue. It's like a purpley, pinky. I've heard some people say magenta. It's a nice magenta. I really don't know what a magenta is, so anyway. Is it purpley pink type thing? I've even heard people say it's fuchsia. I have no idea what fuchsia is. Was it fuchsia? Okay, I'm being sexist here. I'm asking the ladies. Was that fuchsia, ladies? No? Is that wrong? What's so funny about that? Is you have some fuchsia stuff? No? Okay. Purple and salmon? Anyway, okay. We'll go with pink. We'll go with pink, even though it's like a purpley pink. All right. What about the bromethymol blue? What did the bromethymol blue do? It stayed blue. Excellent. How about reactions with magnesium and sodium carbonate? Reactions with magnesium and sodium carbonate. Okay? It did not react. Excellent. Very good. So I did want you to, what were the pH values? What were the pH values? Oh, the 5 concerns me, but I like the 10. what should it be compared to 7? Above 7. So the 5 might concern me a little bit because that's below 7. That's in the acidic range. But 10 is good. That's in the basic range. Okay. There's the universal indicator that you would have learned or used, and hopefully your bases were up here somewhere. Okay. So again, I just wanted to review here the properties. We didn't taste, but if you didn't get a chance to write this down yesterday, you're writing this down right now, okay? Because I do want you to have this in your notes. We didn't taste them, but acids taste sour. Bromethymol blue turns yellow. Phenolphthalein is clear and colorless. Litmus is red. It reacts with metals. It reacts with carbonates. Corrosive, and we didn't check it, but it actually does conduct electricity as well. We didn't do a conductivity test, but we could have. It does conduct electricity, okay? Again, I'm not sure. I think most of you wrote this down, so I think I could go on to the other ones. Properties of bases. They taste bitter. We didn't taste any. Not a good idea to taste them in the laboratory, but if you'd use baking soda type toothpaste, it tends to be bitter. I don't know if you got any of it on your skin, but it is a slimy, slippery feeling, all right? They do have a slimy feel to them. If you've ever helped your parents clean the house, you know why that's so funny? Why is that so funny? Because none of you have helped your parents clean the house. Anyway, I'm just saying, if you're like my kids, that's a joke right there. I made a funny joke. Anyway, if you've ever helped your parents clean the house, and if you've ever used window cleaner like a Windex or something like that, and when you're finished, you should wash your hands after you use those types of products. But if you're finished, I don't know if you've ever noticed, of course you have never noticed because you've never helped, but if you try to help sometime, you'll notice that Windex on your hands is a little slimy. And that's because it has a base in it. It has ammonium hydroxide in it, one of the bases that we tested. And so a lot of cleaning products use bases. That's why they've got that slippery, slimy feeling to them, right? Same with soap. Soap has a little bit of a base in it, and it's got that slippery, slimy feeling to it. Bromethymol blue is blue. Litmus is blue. That can help you remember. Look at base, blue, blue. What's common? B. They all start with B. The way I remember them is base, blue, and then acid is red for the litmus. All right? Actually, I've seen this video before that has this really entertaining scientist from Boston, so he's got a funny accent. And the way that he remembers the color of litmus, it's not the same as the way I do it. I say base blue, and then acid is red. It's the other color, right? He says blue to red, acid. Now, I've never, ever heard the word red and acid as being rhyming words, because I would say red and acid. But he says blue to red, acid. And it's the goofiest thing. Maybe for those who aren't doing the literacy test in the morning tomorrow, maybe I'll see if I can find that video and show you how he says blue to red, acid. The silliest thing. Okay. Anyway, base blue, litmus blue. Sorry, bromethymol blue, litmus blue. They don't react with metals or carbonates. They also conduct electricity. And bases can also be corrosive as well. If you have ever gone back and revisited an old toy that contains batteries, like when I was a kid, I had this tiny little video game that you put the batteries in. It was a Pac-Man game. It was awesome. And then, of course, I forgot about it for who knows how many years. Then I found it again and said, wow, that's the greatest thing ever. So I opened up the back, and what happens to the batteries? They leak, and they get all this kind of white stuff on the back end. Now, what do you think that is? Any ideas? No, it's not lithium. No, you're thinking of lithium-ion batteries, but no, it's not lithium. Yep. Yeah, you might think it's battery acid, but the little batteries that we use in our devices actually don't contain acids. The big batteries we have in our cars, they contain acid, but those little batteries contain a base, all right? So they use the similar properties of acids, but in those batteries. So I don't know if you've ever noticed the electrodes, you know, the metal pieces that you got to push them up against? they're always usually all corroded after that. I don't know if you've ever noticed that. You know, the little metal piece, you go to try to put a new battery in, it doesn't quite work because it's all corroded. Yeah, it's all rusty. So the bases can also corrode just like the acids can corrode. They can do a similar thing. Okay, so if you've got all that written down, then that is awesome. So I'm going to just get out of the end of that PowerPoint because we're done with that one. And I want to talk then now about today's PowerPoint. And again, this is a super short note, but I do want you to write it down. And then we will be getting to our activity, which is to do a neutralization reaction. So today we want to talk about reacting acids and bases together. And we're going to do a similar reaction to what's being demonstrated here. We're going to have a solution in, this time we're going to use a beaker. We're not going to use an Erlenmeyer flask. And we're going to be carefully adding some acid or base to that, and we're going to try to neutralize it. So let's talk about what neutralization is. And so you don't have to write down, again, reacting acids and bases. That's obviously the title of the first screen. But you can write down reactions between acids and bases are called neutralization reactions. Combining acids and bases results in a neutral solution. And the acid and base gets turned into water. And then what we say is a salt. All right. Now, when you read the word salt, you might be thinking of the tasty stuff that you put on your fries. And that type of salt is indeed a salt, but there are different types of salts that can exist. Some will kill you, and some are good for you. We simply call table salt salt because that's the one that we're commonly using. The type of salt that is formed depends on the type of acid and base that is used. So an acid reacted with an equal amount of base can cancel out their acidic and basic properties and result in what we call a neutral solution. Their pHs will cancel each other out, and we will get to a pH of 7. And that's only if we add equal amounts. If we were to add too much of one, then we still might have basic properties if we have too much base. Or if we have too much acid, we would still have acidic properties. It's only if they are reacted in equal amounts. And that's what we hope to do in today's lab. Do we know what this symbol means here? This guy right here, this symbol right there, underneath that arrow. What does that mean? Less than. So acids have a pH of less than 0. Bases have a pH of greater than 0 because of that big end, right? And when you put them together in equal amounts, you get that neutral solution where the pH is equal to 7. Okay? Has everybody done that slide, or Tyson's still working on it?
So, like, to get that, we have an acid that pH level of 1 and then a base with a pH level of 7. I mean, that's at a base. Would that?
No. No. There are two factors that come into play. Number one, remember that the pH scale goes all the way to 14. So the pHs don't add up. If you, 1, right? Because it goes from 0 to 14. The pHs don't add up. You'd have to be equally as far out from 7 than 7 is from 1. So how far out would I have to be? I'd have to be at 13, okay? Now, that only would work if their concentrations are the same. Now, we haven't talked about concentration. I will when we talk about the lab in a moment to tell you how concentrated our acids are. But if I have one thing that is 1/10 the concentration of the other, in other words, weaker, then that won't work. I would need less of the stronger one to balance out the weaker one. It's kind of like if you've got a really small kid on a teeter-totter, right? A little kid on the teeter-totter, and then a big kid, like let's say maybe 2 or 3 grades higher. Then in order to get it to balance, you know how you got to move that little kid in to get it to be a good balance point? I don't know if you've ever done that on a teeter-totter. In order to get them to balance, you got to move the little kid in. So it's the same type thing. If you've got a weak solution, you need a lot more of it to cancel out that stronger solution. So there's 2 effects in there that comes to that. Today's experiment, we're going to be reacting an acid and a base that are of equal concentration. So it should take about an equal amount to neutralize it, if all goes well. Okay? That's a good question, though. Okay, let's just look at some examples of some here, right here, and I'm just going to get you to write them down. That's it. We're just writing them down. That first reaction that you're writing down is the reaction that we're doing today. We're going to take some hydrochloric acid, and we've used some hydrochloric acid in the past. We looked at it yesterday when we did the properties of acids and bases. And we're going to react it with some sodium hydroxide. Again, we used sodium hydroxide yesterday. That's the base that we used. And when they undergo a neutralization reaction, the sodium goes with the chloric of the hydrochloric acid, and it becomes sodium chloride. The hydrogen in the hydrochloric acid goes with the hydroxide, and remember, a hydrogen is this, H, a hydroxide is this, OH, and if I put an H with an OH, what does that get me? An H with an OH? That's not the way we typically write that molecule. What is that molecule known as? A hydrogen with a hydroxide. What is that? It's water. Look at how many H's are in here? 2, H2. How many O's? 1 O. So the water comes from the hydrogens on the acid and the hydroxide on the base. That makes the water. And then the other parts make the salt. In this reaction here, this is table salt. We're actually, in our experiment, going to neutralize it. Then we're going to put the beaker on a hot plate and we're going to let it boil away. And when all the water is gone, we're hoping that we see some salt. We're hoping we see a white opaque solid. Now, unfortunately, because this is a science experiment, we're not going to be able to scrape some off and have a taste, because there might be some other things in there that we don't know about, impure substances, but we're going to see if we get a white solid. If we dealt with hydrochloric acid and magnesium hydroxide, we'd still get the water, but now we would get magnesium chloride. That is a salt, but it's not table salt. I don't know if that would kill you. I don't think so. Magnesium is not toxic. Our body uses some magnesium, but it's not a lot, so I don't think you'd want to ingest too much. If we use sulfuric acid, the H's on the sulfuric acid get together with the hydroxide on the base to make the water, and then the calcium goes with what we know as the sulfate, and you end up with something called calcium sulfate. And we don't ingest calcium sulfate, but it's still considered a salt. Okay? So in the end, we get water and some kind of a salt. So at this point, I'm going to, as per normal, stop my video and put a title on it. Again, for those who are away, or again, you guys can use this as study